question, Eric?
Is there a plan about building the next generation black hole?
That's LHC.
So there's a plan on hold called the International Linear Collider, and there's a group of physicists who have been advocating and pushing for that. It would be an E+E- machine, and all the governments and funding agencies want to see what comes out of the LHC first. There's also a plan to upgrade the LHC to higher intensity. And higher intensity gives you higher energy reach, because what's happening is when you collide two protons, it's not the protons that are in it, say the quarks inside, and they have momentum with some probability distribution. And so if you throw more of them together, then you get higher energy collisions sometimes, just out of probability. And so there's a plan. So Karl and I were last week at a meeting at Fermilab with people from CERN talking about upgrades to the experiment.
As an LHC, keep running always, just one time and stop for a while, and keep running all the time.
You try to run it as much as possible, but you have to do maintenance. You have to do, there's nothing else preventative maintenance. Nothing else by French law, we have to stop and clean the cooling towers. And that's actually a legal requirement.
Now that finally getting to the point where getting it online, there's been a number of, even a year ago, a number of issues that have been run into between leaks, as you mentioned, and PAGSA and things of this sort. What's the tolerance for these types of, I don't want to say failure or mistake, but things that happen? How many times can that happen before you start to agree with your project?
We had better not do this year what we did last year. I mean, I think funding agencies and governments would be really pissed off. There will be little glitches. I mean, it's just too complicated. I mean, what happened last year was, a rapid release of 6 tons of liquid helium with pressure waves and things. I mean, it was bad. And so they're turning the machine on very carefully. And we're not going to full energy first. In the next year, the highest energy will be is 3.5 TeV on 3.5 TeV. And that's just to play it safe.
You expect to get to like 10?
7 on 7, so 14 TeV center of mass. So we'll run at half energy, but it's still many times higher energy than what's ever been done at Fermilab.
And what I was saying earlier, it will take some time for the accelerator to be commissioned so that it can actually go up. So they're going in steps. We hope the steps will be, only a few and won't be that long, but you don't want to break the machine. And they're being much more careful, I think, about this than they would have been a year ago, which is good.
Also a question.
So at this energy level, how much facility can you detect a mini black hole?
Say anything about black holes?
This is going to be on YouTube, so
No. So if I was going to say so the speculation is that gravity is 40 orders of magnitude weaker than the electromagnetic interaction. And there's various mechanisms to explain that difference. And a popular one in the popular press is extra dimensions. If those theories were correct, and if the de Broglie wavelengths of the interactions we're dealing with were shorter than the distance scale of those extra dimensions, then all of a sudden gravity becomes as strong as the electromagnetic interaction, and you can make microscopic black holes. But these are multi-dimensional microscopic black holes. These aren't things that are going to eat you up. Okay? And then the signature for them is Hawking's right, and they radiate. You actually get a very spectacular signature of this democratic emission of particles. You get a spherical wave of particles coming out. It's actually fairly recognizable, and you can recognize and see it. So if that happens, of course, in the press they worry about sucking up the Earth in that. And we have to always keep in mind there's nothing that we do in the LHC that hasn't gone on zillions of times in the upper atmosphere from cosmic rays hitting the Earth. Okay, so if you can make microscopic black holes that ate up the Earth, we shouldn't be here.
So what's the signature of like measuring a supersymmetric particle? Would it just be a particular mass that you expect of the charge? Or?
So the supersymmetric theories are really broad in what they could predict, but they have some general features, and one of them I basically mentioned, this dark matter. If indeed dark matter is a supersymmetric particle that just happens to be the lightest one, so it can't decay to anything else that's supersymmetric. So one of the signatures would be if you make some supersymmetric particles, eventually you produce the lightest one, and it flies out of your detector because it's stable. And it's most of the time these are also not charged particles. The dark matter should not be charged. We're pretty sure about that, or it would interact electromagnetically. So you would see all this missing energy coming out of your collision. So there are other particles like neutrinos that do that, so you can actually study those types of events first. But that's one signature. The other thing that's very common in these models is the way they interact is a bit different. The other forces that are involved in the supersymmetric interactions that can happen. And there is a type of particle which is its own antiparticle, and that leads to events that have, you don't produce an electron and a positron in an event. You might produce 2 electrons or 2 positrons. And that's very rare in the standard model. It would have to happen through some sort of intricate process, and it's very low rate. And supersymmetry, it could happen quite frequently. So people look for these exceptional signatures, lots of missing energy, or 2 leptons with the same sign, so 2 charged particles that you don't expect to find in the standard model event. So there are other ways, but the main way we're going to look for them is you would see a lot of interesting stuff like that happening in the early data. And we should know whether supersymmetry is the solution to some of the problems it was posed to solve, but it will again take a few years at least.
The supersymmetric particles would not interact with like your calorimeter.
If they're stable, they could, yeah. But the dark matter candidates, by definition, would not. So there are different models that predict different kinds of signatures.
One last question, maybe? All right. I guess that's it for the PAGSA panel this week. Thank you very much for your